So this is joint work with Denis Nekipelov and Eva Tardos. In this work, we are interested in a very basic econometric task, which is inferring the private parameters of strategic agents by observing their strategic interactions. More specifically, we're going to be thinking of the following instantiation of this basic economic task, which is inferring the values of players for an item by observing their sequence of bids in some auction for that item. So here's the situation I'm imagining. You have an auction that is repeated over time many times, and you have a set of bidders that are participating in this auction repeatedly, and they have some private valuation for the item that is being auctioned. Now, based on their valuation and based on some beliefs that they might have or some arguing about the competition in the auction, they're going to submit some bid. And here, we as econometricians, we're going to observe this sequence of bids that are submitted in this auction. And based on this sequence of bids that we observe, we want to infer these private values that the players have for this item. Okay. Now, in order to accomplish such a task, one basic assumption that one needs to make is to assume how will players decide what action to take, what bid to submit in this auction, based on their beliefs and based on, I don't know, like how they argue about competition. So the standard approach in econometrics and in economics is to assume that the behavior the players are going to take in each auction is going to be a Nash equilibrium or a base Nash equilibrium if these valuations are drawn from some distribution and are not fixed. But from data, we observe that this Nash equilibrium assumption is not so realistic. And in fact, like we observe that people, here I'm portraying, for example, a sponsor search auction from Bing, and these are the bids of a single advertiser who is participating repeatedly, and these are his bids for different keywords that he's participating in, and this is a period of a week, and we see that he changes his bid very frequently, and this cannot be the case that his value is changing all the time during this period of a week. So if it was a Nash equilibrium, let's say a pure Nash equilibrium, it would predict that his bid would be stable, but this is not what we observe. So advertisers in this auction must be doing something else other than a Nash equilibrium. And in fact, this is reinforced by the fact that most of these advertisers in the sponsor search auctions are using very sophisticated bidding tools to decide what they bid. And these bidding tools, even they claim that they do some dynamic optimization in their advertisement. So they're not doing some equilibrium computation.
Question?
Sure.
Maybe they are learning every day about the values of the others. That's why they are updating.
Exactly.
It doesn't mean you're going to see a stationary behavior.
Exactly. So that's going to be my assumption, that they're learning agents. That they're not doing a Nash equilibrium, but that they're learning agents, and we're going to try to do econometrics. Okay, so this is the main point of the paper, and thanks for introducing it.
Game, yeah.
Okay, so I'm going to assume another model of learning that's not like a sequential Nash equilibrium learning. Okay, so which is based on actually some of your work also. So,
Your picture does not disprove Nash equilibrium. It disproves a Nash with a very
stationary Nash equilibrium. Yeah, it disproves that one.
That was my point.
Exactly. Okay. Yeah. So this is what we're going to assume in this work and try to do econometrics. We're going to assume that the agents are going to use some learning algorithms to play repeatedly in this repeated auction. And so any learning algorithm would look as follows. It would update his strategy based on past observations. So we assume that, people submit some bid at each time step based on the past history of bids that they have observed, of play of all the players. And we're going to make an assumption that implies that maybe in the beginning players don't submit an optimal bid, but over time they will learn to bid something that is approximately optimal. And the main assumption that we're going to make, the concrete assumption we're going to make, is that the bidders are going to use some learning algorithm that achieves vanishing regret. And what do I mean by vanishing regret? I mean that the average utility that they acquired from the bid that they submitted over time is at least as good as the average utility that they would have gotten by playing a fixed bid over time, assuming that all the rest of the players remain fixed at what they did, minus some error term that vanishes to zero as they play more and more games. So this is the definition of a vanishing regret. And why do we make this assumption? First of all, there are many simple algorithms that achieve this no-regret assumption and even stronger conditions than no-regret, such as multiplicative weight updates or regret matching by hard and Mas-Colel.
Sure. Could you go back to the definition? So we want this to hold for all alternative strategy profiles, or what?
For all alternative bids. So you fix what you observed. It has to hold that for any other bid that this player could have submitted, for any other action.
Right, but what is it? It's a no-regret strategy if this inequality holds no matter what.
So the assumption on the learning algorithm would be for whatever sequence, but for our method to work, it has to only apply to the sequence that we observed. But yeah, the assumption is that for any adversarial sequence that you might observe, that the other players are doing, of opponent strategies, you satisfy this condition. And there are algorithms that achieve this strong property. Okay. The other good thing about this no-regret assumption is that most of these algorithms can work even if the players get some very limited feedback about the auction that they're participating in. So they don't need to know anything about the competition or the parameters of the auction. They only need to observe after every iteration what is the utility from the bid that they submitted. And this is important, for example, in applications like sponsor search, where players definitely don't know exactly the auction that's being run and also don't know what are the competitors that are going to participate in each individual impression. Okay. Also, this no-regret assumption is somewhat somewhat minimal requirement from the behavior of the learning algorithm. It just says that you don't regret any fixed bid over time. Most probably, any learning algorithm would satisfy this condition, and it would even satisfy stronger conditions that you might not even regret some slowly changing bid over time or something like that. The last one is that even if you follow the standard econometric approach and you assume that each iteration, the behavior that you observed was a Nash equilibrium of the corresponding complete information game, then such a behavior would also be a no-regret sequence. And so even if you were making that, our requirement is inclusive of that assumption. So it's even more robust assumption to make. Yeah.
Is that true even if what you're observing was a phase Nash equilibrium? So the regrets defined on the realized bids on phase Nash is defined?
Yes, I'm assuming a fixed sequence of bids in this work. So I don't know what would happen if bids are varying over time. Presumably, you would, in the long run, you would also get some equivalence with base Nash equilibrium, but I'm not sure. So here's the main goal. We want to infer private parameters of these participants in this auction, assuming that the observed behavior has a small regret. So this is the high-level approach. If we assume some epsilon regret, then we get a set of inequalities that the observed behavior must satisfy. So it must be for any fixed bid of the players, their average utility must be at least the average utility they would have gotten from this fixed bid minus some error term epsilon. Okay. So this would give a set of inequalities that the unobserved private parameter must satisfy. And if you take epsilon, if you vary epsilon, this would give you the whole set of values that are rationalizable under epsilon regret. So for a fixed epsilon, this set of inequalities would give you the values that are rationalizable for epsilon regret. And if you also vary epsilon, you would get a whole rationalizable set, which is the set of values that are rationalizable under some epsilon regret, for some epsilon. Okay.
You are doing this just once at capital T? Or
yes, just once.
Every period along?
So for now, I'm doing it just once at capital T. And I'm going to mention some future work where we're trying to now to do more a dynamic approach. Then, when we apply this method to data, we're going to because we want to give some interesting summary statistics, we're going to have to pick some point in this rationalizable set, so to give some specific prediction of the value and the possible regret of the player, and I'm going to discuss that when I get to the data analysis part of the talk. So here's the specific model that we're going to use, which is a sponsor search auction setting. So we're going to assume that each player we have a set of advertisers that are participating in this sponsor search auction, and each has some value per click VI, which is his private parameter. Bidders submit some bid to the auction, and they rank according to some scoring rule, which incorporates their bid and some other quality factors, which are very noisy. And then, based on the position, they have some probability of being clicked, and which is typically increasing the position, and then they also pay some function of the next highest bid, which can also be some very complicated function of that bid. The main assumption that we're going to make is that the utility of the player is quasi-linear, which means that for any bid that he submits, his utility is his value times the probability that he's being clicked minus the expected payment he has to make. Now, for such quasi-linear utilities, now everything becomes much easier. The rationalizable set, you can prove that it has much more structure than general utility settings. So all that matters in characterizing the rationalizable set is what is the increase in the probability of click that I would get if I switch to a fixed bid x. So this is like here, assuming everyone else is fixed, this is the average probability of being clicked that I would get if I switch to this x, and this is what I currently got, and you average over all periods. And similarly, what is the increase in the expected cost that I need to make if I switch to this fixed bid x? And now the sequence of bids, this sequence of bids is going to have a regret at most epsilon if the following inequality holds. The increase in my total value, which is my value per click times the increase in my probability of being clicked, minus my increase in my cost has to be at most epsilon. So if it was a purely, if epsilon was 0, then if people were truly best responding, you would get that you cannot increase your value more than you would increase your expected cost by switching to a fixed bid. Okay. Now, an interesting point to make is that even though the rules of each individual generalized second price auction that is being run at each impression is very deterministic and discontinuous, because we're taking an average here, and because there's a lot of noisiness in the ranking score, the average increase in probability of click and in the average cost as a function of a fixed bid are actually going to turn out to be, in most of the data sets that we looked at, continuous functions. So you're going to see some sort of concave increase in probability of click as a function of your fixed bid, and some sort of convex increase in payment. So we're going to make such continuity assumptions in the paper when analyzing the inference properties of this rationalizable set. Okay. So let me now go into some inference properties of this rationalizable set, and then I'll switch to the data and then some simulation data. So these are the rationalizable set is characterized by the set of inequalities which, for any fixed x, these are just linear functions of v and epsilon. So for any fixed x, you're going to get a line, and it says that the value of the player has to be, for any fixed value, for this value to be rationalizable, the regret must be at least some amount, right? So the pair of values and regrets have to lie above this line. And then for another line, you're going to get another feasible region. And so the rationalizable set is going to be the intersection of all these lines, which is going to be a convex function, a convex set, sorry. So the first easy characterization is that this rationalizable set is a convex set. And from that, you can get a lot of leverage. Here is, for example, how these rationalizable sets look from real data, from sponsor sets. And you see that they have this nice continuous form that I assumed here. And what is the leverage that we can get from the fact that the set is convex? Well, we can get that it's characterized by what is called the support function of this convex set, which is basically, if you haven't seen that, is basically for any direction u, you're going to take this line that corresponds to this direction u, and you're going to push it until it touches the boundary of this convex set. And then the value of the support function for this direction u is simply the distance from the origin of this line. Okay? So every convex set is uniquely characterized by its support function. So inferring this rationalizable set from data is equivalent to inferring this support function. And then we saw that the support function of this specific rationalizable set is uniquely determined by the curve that between the increase in probability of click versus the increase in cost. So if you plot this single-dimensional curve that on the x-axis has the increase in my cost for a fixed bid, and here has the increase in my probability of being clicked, and you plot this curve here, this curve is going to uniquely characterize the support function of this rationalizable set. And so inferring this single-dimensional curve is equivalent to inferring the support function, which is equivalent to inferring the rationalizable set. So everything boils down to just inference of this single-dimensional function, which can be done with very few samples of the auctions. Okay, and what do I mean by very few samples of the auctions? I mean that during its period that the player is changing his bid, the player might be participating in many, many auctions, and because it might be too costly to simulate what would have happened in each of these auctions, because we need to go and simulate what would have happened with any other alternative bid, we might want to use like a sample of these auctions, and assuming that during two bid changes the behavior of the auctions are sort of like stochastic. And so we might only want to use a sample of this auction, which is going to introduce some sampling error. And because we've reduced our inference problem, our two-dimensional inference problem, to a single-dimensional inference problem, we're going to have very fast estimation properties as a function of this number of samples that we got. So this is just to make the inference of this rationalizable set computationally much faster. Okay. So now I'm going to switch to the data analysis part. Any questions of the? Okay. So we analyzed 9 frequent bid changing advertisers in Microsoft sponsored Bing, in the Bing sponsored search auction system. And each advertiser has several listings, where a listing is basically a keyword and a bid pair. So I'm bidding this amount for this for appearing in the left-hand side for this specific keyword that is being searched. And we applied this inference method for each listing of each advertiser. And then to get some summary statistics, we use the following point prediction method. So we use the value that corresponds to the smallest multiplicative regret now. And by multiplicative, I mean instead of having an additive error epsilon, put here a multiplicative error lambda, and then find the smallest lambda for which this is satisfied, and output the value that corresponds to this smallest lambda. And why do you use the smallest multiplicative regret? Because then we want to compare these predictions across different these predictions of regret and value across different listings of the advertiser, and the multiplicative version takes away some pathologies, such as that in one keyword the player might have a huge value, and so a small regret might be a small additive regret for such a huge value might be reasonable, and then we're comparing it to a small additive regret for another listing where he has a very small value, and so this is not these are not comparable. But when we go to the multiplicative, it takes away this heterogeneity in values that the players might have for different keywords. Okay, so how does this look like in the rationalizable set? Basically, we're taking this rationalizable set. We're taking a point here which corresponds to the current the current probability of being clicked of the player and the current cost that he's paying. And basically, the smallest lambda corresponds to plotting a line here and taking the largest coefficient until this line touches the rationalizable set. And this is the specific point that we're going to predict over here. Okay. So here are some statistics that we got. So, but first of all, we compare the prediction that we got from this inference method to the average bid of the advertiser, and we get that on average, people bid almost approximately 60% of their predicted value. So the average bid of the advertiser is like 60% of the value that we predict, which is a pretty reasonable conclusion. So that was sort of like reinforcing that we're doing something right here. We also get that the smallest regret has this, the histogram of the smallest regret has this sort of consistently this sort of distribution. There are a lot of listings that have almost zero regret, so they might be best responding, they might be at a Nash equilibrium, etc. And there are several other listings that have large multiplicative regret, ranging from 0 to 50%. So you might say that there's a large fraction that might have arrived at an equilibrium or at an almost best response, and there's another set of listings that are maybe in their learning phase. Okay. Another small observation that we made is that there is a correlation between how much regret you have and how much you said your bid. And we get here that when people are in the learning phase, or when they have high regret, they say their bid more, so they bid less than what they tend to bid when they have small regret. So when they're more in the equilibrium phase. Next, we also did some simulated data. So we to see that at least our econometric approach is valid and when our assumptions are valid, we sort of simulated running GSP over time and we simulated some bidders that are running multiplicative weight updates over time. And then we applied our econometric approach to the observed history of bids, and we saw whether we recovered the values that we put to the bidders when they were running the multiplicative weight updates. Right. So we ran GSP for several iterations. We used uncertain quality scores to simulate what is happening in practice. And then each of these advertisers was applying multiplicative weight updates for some value that we set, which was drawn from some distribution. We also had some advertisers bidding truthfully, some fixed bid to simulate what is actually happening also in practice. And then we applied the inference method to the learning players. And these are sort of the rationalizable sets that we got and the true points of the advertisers. So here, this is a simulation with 5 advertisers, and this is the rationalizable set after several iterations. And here you can see that this is the true point, so this is the true value of the advertiser, and this is his true regret. And what is nice here is that we do get that the true point is actually very close to the tip of this rationalizable set as time goes by. So predicting some value around this tip, even in real data, might be a good point prediction method.
But shouldn't the regret, I'm sorry, I don't
Yes.
understand something.
Yes.
They are using, regret should go to 0.
Yes, so this is...
How do I see that in this picture?
So this is like the rationalizable set over time. So this point is going down to 0.
So
Yes.
time goes down.
Time goes down.
Family of,
Exactly, yes. So these are rationalizable sets over time, and the true point goes down. And it's sort of like pushing the tip of the rationalizable set down. And eventually, when regret goes to 0, you can actually show that with some uncertain quality scores, that the tip will be the tip of the rationalizable set will be the true point. You can actually formally show it for under some assumptions on the noise in the GSP. Okay? That eventually the true point will be the tip. Okay. And so, for example, here's also the distribution. We ran it several times where values were drawn from some Gaussian distribution, and this is the distribution of errors that we get. So if this is the distribution of errors if we predicted the actual tip, which is the smallest additive regret, and this is the distribution of errors if we predict the smallest multiplicative regret, which is what you used in the data. And we see that the smallest multiplicative puts some positive bias on the prediction. So there's some positive bias here, which is not here anyway. So that's one observation, which is happening basically because for very small values of the distribution, there are a lot of equivalent best response bids, and we cannot differentiate these values. And what our econometric method tends to do for these values is overshoot and predict something slightly higher. So this is the true value distribution from these simulations. This is what we predicted based on the smallest additive regret, and this is what we would predict based on the smallest multiplicative regret. And we almost get the right shape, subject to these pathologies in the smallest value region. So let me conclude. So the data shows that players have a small but non-zero regret and are frequent bid changers. So if we want to handle such data sets, we need to use some learning model in our econometric methods. And so we proposed an econometric method based on this no-regret learning theory. And there are several next steps that one can take from this. So currently we're looking at some more dynamic analysis of these rationalizable sets and whether the regret is actually going to 0. Another very hard task is to actually do some inference on the actual learning algorithm that the users are doing, or some sort of like abstract model of the learning algorithm, and try to fit some update rule for the advertisers. Another approach that we're taking is to directly infer some properties of the outcomes rather than the values directly. So you might want to infer how efficient the outcome is without actually inferring the true values, and get some bounds on the efficiency from the data. And we're exploring with Daryl and Denis Nekipelov whether we can do such things by dropping some of our assumptions for this paper, such as the fact that the values were constant over time. So we are looking at whether we can handle both learning players and valuations changing over time, and predict some price of anarchy from data, which is going to bridge sort of the gap between the worst case price of anarchy guarantees from theory and econometric guarantees from data. One could also look at other bidder objectives other than this quasi-linear utility model. So this is So there are several other objectives that advertisers are interested in, such as return on investment and stuff like that. So you might also want to you could apply the no-regret learning approach to other bidder objectives. And I think the holy grail in all this line of work is sort of being able to predict long-term effect when we change the auction from one to another, and without making the assumption that people are going to be at equilibrium. So sort of like, even if people are learning over time, we want to see what is the long-term revenue effect or efficiency effect if we change from this auction to another auction. And I hope that online learning theory could be a useful tool at taking a stab at this like very difficult task. Thank you.
You said that people shape their build more when they are uncertain, when they are still learning. So should we take that to mean that the risk aversion dominates the incentive to explore and so on?
That's my interpretation of it. Yes, that they are more uncertain what's happening, so I'm more conservative.
And how do you know that when you see people with high regret, they're just people who are not satisfying the assumptions of your model, and so the inference is wrong? Maybe,
yeah. So people with high regret might not be doing no regret. So that the dynamic analysis would actually is exactly going to tackle this fact. At least if I see that their regret is vanishing, sort of, then they are still in inside the model. So I think that's going to be the answer to this question, I guess. Yeah.
Okay. Thank you.
Thank you.